Hey, happy holidays, everyone. This is your struggling CS student, and today I'll be doing another LeetCode problem. So, yeah, let's get into it. Anyway, I couldn't do this question on the 24th. It was very hard, and I had some personal issues to resolve, some personal tasks to attend to. Then the day after that, this question is actually relatively straightforward, so I just spent like 30 seconds going through it. Basically, you're given a tree problem, you're given the root of a tree, and you need to find your largest value in this tree row. So as you can see in the tree, for each row, each level, you just pick the max, and then you append it to the output, and you get your answer. So it's really straightforward. As long as you know breadth-first search or level order traversal in a tree, then you can just process a level and you just take the max and append it to the answer. So that's how you solve this problem. It didn't take me more than 10 minutes, I imagine, to solve this. So with that said, let's take a look at today's problem, 494 target sum. So actually I've solved this problem before, but let's take a look again. I've not done this problem yet today, as you can see. Yeah, I don't have the fire symbol here, so let's take a look. Target sum. So you're given an integer array nums and an integer target, and you want to build an expression of nums by adding one of the symbols, whether positive or negative, before each integer in nums, and then concatenate all the integers. For example, so if nums equals to 2, 1, you can add a plus before the 2 and a minus before the 1 and concatenate them together to build the expression plus 2 minus 1. Now return a number of different expressions that you can build which evaluates the target. Okay, let's take a look at some examples. Target is 3. There are 5 ways of concatenating nums. Okay, so you can put negative here, positive, 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 positive. Okay. Yeah, okay. Nums equals 1, target equals 1. Okay, fair enough. So when we take a look at the input size, there's only 20, so that actually gives a very strong hint that we should probably consider backtracking. And looking at the problem, we probably can only use backtracking because we have to basically find all the possibilities that nums can give us, and we have to evaluate the expression. All right, so let's take a look at the other constraints. Nums can be 0 or a positive integer, and then the sum of nums is always sum of nums. Isn't this still the same? Oh well. Yeah, the sum of nums of I is from 0 to 1000, and then the target is negative 1000 to 1000. Okay. So conceptually, how would the problem look like? I would say conceptually, well, suppose we have some numbers here, let's say A, B, C, and then let's say and our target is Z, all right? Doesn't really matter, but we will have to go through all the list of possibilities. For example, we can put a plus here, we can put a minus here, or we can put a plus here, minus here, or we can even put a minus here, plus here. You get the idea. So it will probably involve some sort of backtracking. So initially, we can build out our tree of possibilities. Initially, we will have the empty expression, and for the first number, let's use the same example. So A, B, C, D. What we can do is, well, there's only really two options here. We can either add a positive sign to it, or we can make it negative. And then for the next one, it's the same thing. For the next number, we can either add positive sign to it or negative sign to it. Oh, negative B. Likewise for here, do positive B, and then let me do that a little bit nicer. And then negative B. You get the idea. All the way until we reach the end of the tree of possibilities. When we reach a leaf, for example, maybe like plus D or something, right? Then we have to evaluate whether the sum is equals to D, whatever the expression is. So yeah, very straightforward backtracking. Now the other consideration we have to think about is whether we can prune the tree of possibilities. For example, maybe at this point, suppose at this point, is there a way, without exploring like plus c minus c, etc., etc., is there a way that we know for sure that this wouldn't lead us to any other answers? Like it's impossible after we have reached this point to construct an answer out of these subtrees. And I think the answer is no, we can't actually prune this tree. Can't actually do backtracking with pruning because could be the case that maybe a plus b, using this example again, maybe a plus b does exceed z in some way, but however, by a plus b, maybe minus c and minus d actually give us the answer. And at this stage, we just can't evaluate whether this is true, which means what? Which means we have to explore all possibilities. We can't prune it. So, right, let's get into it. Let's code it up and see if I can express my idea as a program. So usually for backtracking problems, you solve it recursively because the tree of possibilities is modeled as a tree, and therefore recursion is usually a good way to process tree problems. Right, so you define some sort of base case here, which I will not define it yet, and you need to do some processing here, which I will not do yet. It's just a template, sort of, I guess. So we need to think about the variables we have to keep track of as we backtrack. I think initially I'll just think about a global variable. Let's say this is the result, so we return result in some way, and then we have to backtrack, right? Now when we backtrack, of course, we have to think about the current state, probably some sort of list, and then some sort of index to indicate the starting position or the next number we're considering. I just put 0 here because we're starting from the first number. So now we can think of the base case. The base case is because, well, like I said, there's no pruning to be done. Then what we have to do is the length. Okay, before that, this is the current state of the list, or basically a path, some sort of path down to the left, right? As we are building the expression up, or building expression, yeah, building expression up, correct. So if the length of current is greater than or equals to length of nums, then we have a possible solution. So we only do this if the sum of current is equals to target, right? Else they'll never return. Here we have the index that we're keeping track of. Additionally, you could put the cumulative sum here as an additional state if you want to keep track of that. It really depends on how you want to do it. And here in our processing, what do we have to do? So for I in range from the starting index or number that we're considering to the end of the input, we can add a positive sign first, which is just the number itself. So that would be nums of I. Nums of I. Then we can backtrack from there. Backtrack current and I plus 1 because we're considering the next number. Then this is the backtracking step. Then I think we just do the same thing again as said. This time around we add a negative to it. We add a negative to it because then now we're constructing the case where it's we're adding a negative to the current number that we're considering. I think that should be it. Let's give it a spin. Okay, well, that was embarrassing because we're using a global variable. We have to put non-local here so that the function can modify this variable, and it's not as if it's creating a new variable here. So it passes the base case. The sample test cases. Maybe we can add more test case and see if it works. Let's do an impossible case. So maybe like this. We can do 2, 3, 4. Then let's make, I don't know, maybe 3. Let's say this is 3. It's 1, 2, 3, 4. Are the numbers? Oh, the numbers don't have to be unique. Let's do this again. maybe add a 0 and a 9, and let's see if it passes. I'm quite confident it should pass. Okay. So it passes the sample test cases. I'm just thinking if I would encounter a time limit exceeded scenario or TLE. I don't think so. I don't think so because, yeah, like I said, there's no way to, you have to construct the candidate solution out. And what I mean to say candidate solution, I mean really it's an expression all the way down to the leaf. Because there's no way to prune, you can't prune it. Yeah. Okay. So let's say this, I'm going to go with this as my solution. And what's the time and space complexity here? So actually the time complexity is 2 to the power of n, where n is the size of the input. And why is it 2? Well, because at each step, so this is the time complexity. Because at each step, let's say this is the first number we're considering, at each step we are exponentially exploring 2 possibilities, and then here we're doing 2 again, right? Then here we're doing 2 again, you get the idea. So at each step, this is, let's say, this is the index, and this is initially 0, and then this is index is equals to 1. Then you can see that at each step of the way, the number of work that we're doing is growing exponentially. But then what is the size, or rather what's the space complexity? Well, the space complexity is n. Space complexity is n because this is the space taken by the call stack as we go through down to the leaf or the possible candidate solution that we're considering in our backtracking. So it's O(n) for the stacks, the call stack space is also O(n) as we are keeping track of the current state, so you can think of it as maybe n plus n, right? And I think that's it. That's it. So I'm gonna lock it in as my answer. This is my answer. Let's hope it's correct. So I'm submitting it. Oh, what? I'm getting TLE? Really? What? Okay. Damn. Okay, I did not expect that. Why do we get TLE? What's the answer? Now that's unfortunate. God dang it. Okay. All right, now I have to think about it. Yeah, I have to think about this one. Hmm. What if I just run this here? Will it still time TLE? Looks like it. I still get TLE. What the hell? I'm thinking if it's possible to use dynamic programming. No, there's no way. There's no way. Using deep, I don't see how we can reuse sub problems to help us solve, uh, well, the original problem. Hmm. Maybe you can do some sort of compression. There's no way. What I mean by that is we can compress all the zeros together. That makes it a little bit more complicated. I'm thinking of another way, but I don't think it changes anything. I could be wrong though. I could be wrong. So you just maintain two lists? Really? I don't think so though, but it's no harm trying since I'm kind of stuck. If sum of current 2 is equal to target, L0, so you do current 2 instead. And you do backtrack current 2, I plus 1. What happened? Invalid syntax. Oh, 1. Okay, now it's just straight up wrong. Ooh. Interesting. I actually don't know why this is the case. What? Why does it only run like once? That is crazy, yo. Okay, it's not running once, it's actually running a lot of times. $20? Are there really 20 elements? Okay, yeah, maybe, yeah. Okay, that's a bummer. Oh, I see, I see. I think I got it. I think. I could be wrong. So actually there is a way to optimize this, and there is a way to prune it, which is if you sort nums first. Sort nums first in ascending order. So let's say you got some sort of numbers here, A, B, C, D, right? And let's say you're evaluating the Z. Well, it doesn't, let's say this set of numbers originally was not sorted. So we don't, okay, make it a little bit visually understandable. Maybe it's B, C, then A, B, D, A, C. So you see that actually this is unsorted. And then in this case, when you are considering, let's say, this particular expression, you will know that you can't know for sure if adding future numbers is gonna, is that really true? Maybe that's the case for addition. Yeah, actually, never mind. I was thinking like if you can sort it, so you sort it like this, and then, at this point, Actually, it's true. It could work. Could work. So if you are adding numbers, yeah, let's say this is the target and you sort it, right? And at this point, if a plus b is really greater than z, there's no point in adding this. There's no way we can actually derive an answer that is like this when we talk about strictly adding numbers. So actually we can prune one side of the tree. What we can't do is, that's what we can't do. What we can do is, if we know that this is greater than z already, then we have to take this path. We have to take this path. We actually can't take a plus b plus c. Okay, yeah. Whereas if you leave it unsorted, if it's unsorted, then, well, you kind of have to consider everything. So I think if we sort nums.sort, then let's just put the result here. And what we do is, okay, then in that case, it's better if we keep track of the cumulative sum right now. So we don't have to redo the calculation every time. So we say the current sum plus 1 if the current sum is equal to the target. Then now we can say, if current sum plus nums of I is less than equals target, then we do the backtracking. Likewise here, if the current sum minus nums of I can target be negative? Target can be negative. Target can be negative. Maybe we have to do something like this. I'm just making a guess. Just making a guess. Less than equals to target. Then we do the backtracking. And this is minus, now minus equals. And also when we backtrack, we have to add actually have to modify the current sum. Likewise here. Or am I cooking or am I getting cooked? Still so slow. That's not good. Alright, looks like I got cooked. It's the same thing. Okay, but conceptually is it correct? No, even conceptually it's wrong. 4 and 0. Why is this like that? Oh, okay. I think I know why. I see we are cutting out other potential solutions. So for example, in this current solution here, if I do a case where I add 1, 1, 1, and actually we have reached the target, we wouldn't actually consider this solution where it's like, oh shit, it's like this one. We fail to consider this current case, right? I think so. The case where it's 1 plus 1 plus 1 plus 1 and 4, then it's 4 minus 1 and get 3. Yeah. Oh snaps. Let's see if that is actually the case. I think we'll miscount some. That's the problem. Actually, we can just do it here. There's only 4. Okay. One, 1, 1 minus 1. Yeah, you see, yeah, this is exactly what I was talking about. We missed the case where we missed this configuration, right? It's four ones and a minus one at the end. Okay, well, never mind. I just got cooked. This doesn't work. Oh my lord. I'm just taking the sample test case. Wait, I one-shot killed this? Oh my teens. Okay. So sorting doesn't even help us here. I could check the cumulative sum still, that's fine. Do we really just compress it? Sum of nums of I is less than 1,000. Actually, we don't really need this, I think. Oh, we do need, never mind. Oh shit. Okay. How can we optimize this? Hmm. Oh my teens. I'm so stubborn. I think I'm cooked. I'm gonna hold on for maybe 10 more minutes. Holy shit. Why, why is this failing? Or what can we do to optimize this? This is hard. Fuck. I'm thinking if there's a DP component to it. Well, initially I said I couldn't find a DP component to it, but maybe there is. Maybe there is. Maybe there isn't. I don't know. Shall see. Maybe there is. Holy shit. Wait, really? Okay, so the rectangles I'm drawing represents the subproblem, right? Really? God damn. How many ways can this evaluate the target? Let's say this evaluates the target x times. This evaluates the target x times. So how does this help us? How does this help us? And there's also the negative portion to it. So we have two subproblems here. Can we really use the computation? Not really. How? How do we reuse the computation that we done for these subproblems? And it's not like we can figure out the answer just using the subproblem itself. So that's 0, 0, 0, 0, 1. How many of these ways evaluate to 2? If our target is 2, right? Just as an example. Target is 2. Well, obviously, in this case, there will be 0 times. Okay, let's say this is 1. That means what? You can put plus, plus, plus. In fact, this must always be a plus. That's one way. This could be minus. That's 2 ways. This could be plus. This could be minus. That's 3 ways. So I'll take this off. 0, 0, 1. Target is 1. There are four ways. Okay. Plus, 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 minus, minus, plus. Oh, minus, minus. I see. So there are four ways. Okay. Suppose we know there are four. So we have four ways here. And how does this help us? Let's say we're at this position. The hell? How does knowing that there are four ways to make this help us? So add another zero here. What does that mean? That means this could be plus, this could be minus. Plus, minus, plus, 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 minus, minus, plus, and minus, minus. So we'll add another 8 to this. Oh, the total is 8. Am I getting somewhere? So it's basically, these ones can change to the power 3. And you get 8. That means suppose we know the sum of this, which is 1. And if we add this, and that equals to the sum, that means, yeah, but what? How can we, but this might not be 0. You know, this could be like 2 or something. Unless we always keep track of 2 sums. There's no way. Okay, I give up. Oh my teens. I solved this before and it was a one-shot kill. And what I mean by that is I solved it the first time and now I couldn't. So that's sad. Dynamic programming. Brute force is which is what I did. This Python solution gets a TLE. Recursion with memorization. Okay, so it's actually DP. Calculate ways. So how do you memorize it? With the current index and the current sum. N times total sum. 2D DP. It's actually DP. Oh my TNs. What is this? I don't know what's that. Okay, so brute force goes TLE. Just saying that if we memorize this, okay, we need to do a custom memorization then. Because in Python, we can't, this is a mutable data structure, then you can't cache it because, how should I say, for Python, they need the state to be immutable, I guess, something like that. So we have to store the answer somehow. So memo of index of current sum is equals to what? It's equals to current sum. Wait a second. This is the number of ways. So I guess we will have to return ways. and return this. Maybe you don't need that. Maybe just like that. Goes to 1. Really? That's the current index. Then we do index plus 1. Oh shit. This again. Key error. Oh, this is return 1 by the way. Oh, this has to be a default dict. Int. And we also need to do the memoization part, which is if memo index of current sum is greater than 0, then we will want to return this. In object is not subscriptable. Huh? What the hell? What the hell is this? Default dict of int, and actually it should be plus equals 1. Huh. Alright, let's see what memo is. Wait, what's going on? Oh, okay, I see. That's a stupid mistake. Basically, it's not a 2D dictionary. This is the key itself. Okay. I'm still getting fucked. Oh, okay, I see. Okay, it's all wrong. Nice. Oh. I'm overcounting it so much. What the hell? Oh shit. Yeah, not this. Six. Ugh. If maybe okay, maybe not a default dict, which is a dictionary. Really? Okay. Oops. Okay. It's the same. Um. All right. Let's see how they do it. Fuck. Uh, uh, oh, wait. Oh, I'm dumb. I'm dumb. Basically, we didn't store it. Oh my days. Okay. Is that? I feel like it's still wrong as fuck. Yep. Um. Okay, fine. Alright, this was depressing. How did I do it last time? Oh, it's actually DP? Oh, shit. Okay. I'm tracking the current sum going from the end. If the end of this minus this equals to target. Oh, okay. Basically, if we add the current number and this equals to target, this reverts to 1. Or if we minus the number, equals to target. Okay. I minus 1 as we go towards 0. This is positive. It's cached. Really? Okay, I have to read this more, man. Um, yeah, I'll read this when I get back home. But anyway, this has been a long one. Thanks for watching, guys. This is a struggling CS student here, so happy holidays, and have a great one ahead.